In March of 2026, something is going to happen to Jupiter that has never been observed in recorded human history. And what makes it truly extraordinary is not the encounter itself, but the mathematical impossibility of how precisely it's been calculated to unfold. An interstellar visitor, a comet that came from beyond our solar system, is heading directly toward the largest planet in our cosmic neighborhood, and the numbers describing its trajectory have left astronomers staring at their screens in disbelief, not because of what it will do to Jupiter, but because of what those numbers reveal about the journey itself. Now, before your mind races to catastrophic collisions or planetary destruction, let me stop you right there. This is not about danger. This is not about an apocalyptic impact that will shatter worlds or disrupt our solar system's delicate balance. Jupiter is going to be perfectly fine. Earth is going to be perfectly fine. In fact, if you were standing on Jupiter's cloud tops during this encounter, assuming you could survive the crushing atmosphere and radiation, you might not even notice anything happening at all. The distance between this interstellar comet and Jupiter's surface will be vast enough to ensure complete safety for the giant planet. But here's where it gets interesting, where the story shifts from sensational headlines to genuine scientific mystery. This comet, designated 3I Atlas by the astronomical community, is approaching Jupiter at a distance and angle so precisely calculated, so mathematically refined, that it's threading what scientists call a gravitational keyhole, with an accuracy that natural orbital mechanics rarely produce. Think about throwing a dart from across a football field and hitting not just the bullseye, but a specific microscopic point within that bullseye, and doing it while blindfolded, after being spun around with the dartboard moving. That's the level of precision we're witnessing here. And this precision, this mathematical elegance in the trajectory, is what has transformed a simple planetary flyby into one of the most intriguing astronomical events of the decade. Because when something moves through space with this kind of exactitude, especially something that originated from beyond our solar system, from the vast interstellar darkness between stars, it raises questions that go far deeper than simple gravitational mechanics. It makes us wonder about the forces that shape this path, about the invisible hands of physics that guided this cosmic traveller across light years of empty space to arrive at Jupiter's doorstep at precisely the right moment, at precisely the right angle, moving at precisely the right speed. You've probably seen the headlines. You've probably scrolled past the viral posts claiming that Jupiter is in danger, that our solar system is about to witness some cataclysmic collision, that this interstellar intruder will somehow devastate the king of planets. And I understand why those headlines exist. Fear sells. Catastrophe captures attention. The human brain is wired to respond to threats, to dangers, to the possibility that something terrible might unfold. But what if I told you that the truth, the actual scientific reality of what's happening, is far more fascinating than any fictional disaster scenario could ever be? What if the real story here isn't about destruction, but about discovery? What if the shocking part isn't what 3I Atlas will do to Jupiter, but what Jupiter's encounter with this visitor will reveal about the nature of interstellar objects, about the forces that can steer comets across the cosmic void, about the precision that's possible in a universe governed by gravity and momentum and forces we're still working to fully understand? Stay with me. In the next several minutes, we're going to peel back the layers of sensationalism and dive into what's actually happening as this interstellar comet approaches its final major encounter before leaving our solar system forever. We'll explore why the trajectory is so precise, what non-gravitational forces might be at play, what Jupiter will actually experience during this flyby, and why March 2026 represents a unique opportunity to study something we've never had the chance to examine this closely before. We'll separate the viral myths from the verified science, and by the end, you'll understand why this event matters not because of danger, but because of what it teaches us about the universe we inhabit. Because here's the thing that most people miss when they see these dramatic headlines. 3I Atlas has already passed Earth. It flew by our planet back in December, coming closer to us than it will ever come to Jupiter, and nothing catastrophic happened. It passed Mars in October, threading through the inner solar system like a cosmic needle moving through celestial fabric, and the red planet continued its orbit completely undisturbed. This comet has been travelling through our solar system for months now, and every prediction, every trajectory calculation, every mathematical model has proven remarkably accurate. The precision isn't just impressive, it's almost unsettling in its exactness, and that precision, That mathematical perfection in its path is what transforms this from a simple, astronomical event into a genuine mystery worth investigating. Because while we understand gravity, while we can predict how objects move through space under gravitational influence, there's something else happening here. There's a component to this comet's trajectory that doesn't fit neatly into pure gravitational models. Scientists have detected what they call non-gravitational acceleration, subtle changes in velocity and direction that suggest forces beyond simple orbital mechanics are influencing this visitor's path. Now, before we go any further, before we dive into the physics and the mysteries and the unanswered questions, I want to hear from you. If you're ready to uncover what's really happening, if you're curious about the science behind this precision, if you want to understand why astronomers are paying such close attention to an event that poses no danger whatsoever, hit that like button right now. And drop a comment telling me what you think is guiding 3I Atlas through our solar system. Is it purely natural physics, the outgassing and jets that all comets experience? Or is there something more at play, some aspect of celestial mechanics we haven't fully accounted for yet? Your thoughts matter because this is the kind of mystery that science thrives on, the kind of question that pushes our understanding forward, and I genuinely want to know what your instincts tell you before we dive deeper into the evidence. So let's begin this investigation together, starting with the most important question of all. What does everyone get wrong about this encounter, and why does the truth matter so much more than the fiction? The internet loves a good disaster story, and when it comes to space, the bigger the catastrophe, the more clicks it generates. So when news started spreading about an interstellar comet heading toward Jupiter, the predictable wave of sensational content began flooding social media. Videos with dramatic thumbnails showing Jupiter exploding, articles with headlines screaming about solar system chaos, posts claiming that this encounter would somehow disrupt planetary orbits or send Jupiter careening through space like a cosmic billiard ball struck by an impossibly fast cue. And I get it. I understand why these narratives gain traction, because they tap into something primal in us, the fear of cosmic forces beyond our control, the anxiety about our fragile place in an incomprehensibly vast universe. But here's what you need to understand right from the start. 3I Atlas is not going to collide with Jupiter. It's not going to crash into the planet's atmosphere, it's not going to skim across the cloud tops, it's not going to make physical contact of any kind. The distance at which this comet will pass Jupiter is enormous, measured in terms that make even a close approach seem remarkably distant when you understand the scales involved. To put this in perspective, imagine you're standing in the middle of an empty football stadium and someone rolls a marble past you from the opposite end of the field. That marble passes you at a distance that feels close in the context of the stadium, but you're never in any danger of being hit. You're never going to feel the marble brush against you. You're simply observing an object moving through the same general space you occupy. That's essentially what's happening here, except instead of a stadium, we're talking about the gravitational sphere of influence around Jupiter, a region of space where the planet's gravity dominates, but where actual physical proximity is still measured in vast distances. 3I Atlas will pass through this region, this gravitational neighbourhood, but the comet and the planet will remain separated by a gulf of space that ensures complete safety for both objects. Jupiter's massive atmosphere, its swirling storms larger than Earth, its powerful magnetic field, none of these will be affected in any meaningful way by this visitor's passage. And yet, the myths persist. They persist because collision stories are exciting. They persist because the human imagination loves to picture cosmic catastrophes, loves to envision what would happen if worlds collided, if celestial objects smashed into each other with planet-shattering force. Movies have conditioned us to expect these scenarios. Disaster films have taught us that when objects from space approach Earth or other planets, impact is inevitable, destruction is guaranteed. But the reality of celestial mechanics is far more subtle, far more elegant, and honestly, far more interesting than any fictional collision could ever be. Here's the truth that gets lost in all the sensationalism. Space is astonishingly empty. Even in our relatively crowded solar system, the distances between objects are so vast that actual collisions are extraordinarily rare. Comets and asteroids have been passing through this region for billions of years, and the vast majority of them complete their journeys without ever making contact with any planet. They swoop in from the outer reaches, curve around the Sun or one of the giant planets, and head back out into the darkness, their paths determined by gravity but their destinations lying in the empty spaces between worlds. 3I Atlas is following the same pattern. It entered our solar system from interstellar space, carrying with it the momentum from its previous journey through the galaxy, and it's now making its way back out again. The Sun's gravity bent its path. Jupiter's gravity will bend it again. But these are gentle influences compared to the comet's overall velocity and trajectory. Think of it like a car on a curved highway. The road guides your direction, but you're not crashing into the pavement, you're simply following the natural contours that the engineers designed. Gravity is the engineer here, and the highway it's designed is a smooth curve that takes 3i Atlas past Jupiter, not into it. Now, I know what some of you might be thinking. If there's no danger, if Jupiter is completely safe, if this is just a routine flyby despite coming from beyond our solar system, then why does this matter? Why are scientists paying attention? Why are major observatories preparing to watch this event? Why are mission teams discussing whether spacecraft like Juno, which orbits Jupiter, might be able to contribute observations during the encounter? And that's the perfect question, because it reveals the fundamental misunderstanding at the heart of all this viral content. The significance of this event has nothing to do with danger. It has everything to do with opportunity. See, interstellar objects, visitors from other star systems, are incredibly rare. We've only confirmed a handful of them in all of human history. The first one we recognized was Oumuamua back in 2017, an object so unusual in its properties that it sparked debates that continue to this day. Then came Borisov in 2019, the first confirmed interstellar comet, an object that looked and behaved much more like the comets we're familiar with from our own solar system. 3i Atlas is only the third confirmed interstellar object we've identified, and it's giving us an unprecedented opportunity to study how these cosmic travelers interact with planetary gravity wells. When it approaches Jupiter in March of 2026, it won't be destroying anything, but it will be participating in a natural experiment, a real-world demonstration of gravitational physics at scales and velocities we rarely get to observe this closely. Jupiter's immense gravity will tug on the comet, altering its trajectory, changing its velocity, demonstrating principles that we understand theoretically, but rarely see play out with such clear observational data. This is why the myths are so frustrating for scientists and science communicators, because every headline about planetary destruction, every viral post about solar system chaos, every thumbnail showing Jupiter exploding is drowning out the actual fascinating story. It's burying the real mystery under layers of fictional drama, and in doing so, it's robbing people of the chance to understand something genuinely extraordinary. The truth is that 3i Atlas represents a messenger from beyond our cosmic neighbourhood. It formed around a different star, in a planetary system we may never identify, and it was ejected into interstellar space through some process we can only speculate about. Maybe gravitational interactions with giant planets in its home system flung it outward. Maybe the death of its parent star disrupted the orbits of everything around it. Maybe it was wandering the galaxy for millions or even billions of years before happening to pass through our small corner of the Milky Way. We don't know its full history, we may never know, but what we do know is that it's here now, giving us a fleeting window to study something from beyond our solar family. And the fact that it's approaching Jupiter with such precise trajectory, that's not a sign of danger. That's a sign of something even more interesting. It's a sign that forces beyond simple gravity are at work, that this comet is responding to influences we need to understand better, and that March 2026 will give us data we've never had access to before. But to appreciate that data, to understand why it matters, we first need to know what this visitor actually is, where it came from, and what journey it's undertaken to arrive at Jupiter's doorstep at this exact moment in time. To understand what makes this March encounter so significant, you need to understand the journey that brought 3i Atlas to our solar system in the first place. This is not just any comet. This is not some icy remnant from our own Kuiper belt making a routine pass through the inner planets. This is a traveller from the vast interstellar wilderness, an object that spent an incomprehensible amount of time drifting through the darkness between stars before gravity caught it and pulled it into our cosmic neighbourhood. The comet originated somewhere in the direction of the Sagittarius constellation, though pinpointing its exact home system is impossible with current technology. Think about that for a moment. Somewhere out there, perhaps dozens or even hundreds of light years away, there's a star system we've never seen, orbited by planets we'll never visit, and that distant system is where this icy wanderer began its existence. It formed from the same kind of primordial material that built our own solar system, dust and ice, an organic molecule swirling in the cold darkness around a young star, but it did so in a completely different cosmic environment, under the influence of different gravitational forces, perhaps even with a different chemical composition than the comets we've studied throughout human history. At some point, something happened. Some event, some gravitational interaction, some cosmic disturbance ejected this comet from its home. Maybe it was a close encounter with a gas giant, a planet similar to Jupiter but orbiting a different star, and that encounter's gravitational slingshot flung it outward, with enough velocity to escape its parent star's gravity well. Maybe it was the death throes of that star, the violent expansion or explosion that disrupted every orbit in the system and sent countless objects tumbling into interstellar space. Or maybe it was something more gradual, subtle gravitational perturbations over millions of years, slowly nudging it outward until it finally broke free and began its lonely voyage through the galaxy. We don't know which of these scenarios is correct. We may never know. But what we do know is that this comet then spent an enormous span of time travelling through the void between stars. Not weeks, not months, not even years, but potentially millions of years drifting through space at velocities we can barely comprehend, moving through a darkness so profound that the nearest star would appear as nothing more than a bright point in an endless black sky. During this journey, it encountered no planets, no gravity wells strong enough to capture it, no warmth from any sun to vaporize its ices and create the glowing tail we associate with comets. It was simply a frozen chunk of ancient material, preserving within its structure the chemical fingerprints of the star system where it formed, carrying evidence of cosmic processes that happened before our sun even existed. And then, by pure chance, by the random geometry of galactic motion, its path intersected with our solar system. The sun's gravity, weak at interstellar distances but growing stronger as the comet approached, began to curve its trajectory. This wasn't capture in the traditional sense. The comet's velocity was too high for the sun to trap it in a permanent orbit. Instead, what happened was a gravitational bend, a hyperbolic trajectory that would bring 3I Atlas sweeping through the inner solar system in a single dramatic pass before flinging it back out into interstellar space, this time aimed in a different direction, toward a different region of the galaxy. That hyperbolic trajectory is key to understanding what's happening. It means this comet is just passing through. It's a tourist in our solar system, not a permanent resident. It's going to make this one grand tour, curve around the sun, interact with a few planets along the way, and then disappear back into the cosmic darkness from which it emerged, never to return. This is humanity's one and only chance to study this particular visitor, our single opportunity to gather data about an object that carries information from beyond our solar neighbourhood, and we're making the most of that opportunity. The comet has already given us two major observational events. Back in December, it passed relatively close to Earth, close enough that telescopes around the world were able to track it, photograph it, analyse the light reflecting off its surface and the gases streaming from its nucleus. That December flyby gave astronomers their first detailed look at this interstellar visitor, their first chance to measure its composition, estimate its size, and calculate its precise trajectory with the kind of accuracy that only close observation allows. Then, in October, it passed near Mars. The red planet, with its thin atmosphere and cold desert surface, watched this cosmic traveller sweep by at a distance that, while vast in human terms, was close enough for Mars-abiting spacecraft to potentially contribute observations. That encounter gave us another data point, another piece of the trajectory puzzle, another confirmation that this comet's path could be predicted with remarkable precision. Now, Jupiter represents the final major waypoint before departure. After March 2026, after this comet threads through Jupiter's gravitational sphere of influence, there will be no more close approaches to any planet. 3I Atlas will be heading outward, toward the outer solar system and eventually beyond, its path taking it in the direction of the Gemini constellation, but at such a high velocity that it will leave the sun's influence entirely. It will become, once again, an interstellar object, drifting through the galaxy until perhaps, millions of years from now, it encounters another star system and begins this process anew. This is why the Jupiter encounter matters so much. It's not just the last major observation opportunity, it's the most significant one. Jupiter's enormous mass, its powerful gravitational field means that this flyby will test the comet in ways that the Earth and Mars encounters could not. Jupiter's gravity is strong enough to noticeably alter 3I Atlas's trajectory, to change its velocity, to demonstrate in real time how interstellar objects respond to gravitational interactions with giant planets. And because we've been tracking this comet so carefully, because we have months of observational data already collected, we'll be able to measure those changes with unprecedented precision. But here's where the story takes its most interesting turn. Because when scientists looked at all that accumulated data, when they processed all those observations and refined their trajectory calculations, they noticed something unusual. Something that transformed this from a simple observational opportunity into a genuine scientific mystery. They noticed that the path 3I Atlas is following, the precise trajectory that will bring it past Jupiter in March, is threading through space with an accuracy that pure gravitational mechanics struggles to fully explain. And that precision, that mathematical elegance, is what we need to examine next, because it's where the real shock value of this story reveals itself. So let's address the question that the title of this video promises to answer. What will 3I Atlas actually do to Jupiter when it makes its closest approach in March of 2026? And I want to be completely clear and direct with you right from the start, because the answer is simultaneously simple and profoundly revealing about how celestial mechanics actually work. 3I Atlas will do absolutely nothing to Jupiter, not a single thing. Jupiter, the massive gas giant that contains more mass than all the other planets in our solar system combined, that generates its own internal heat, that hosts storms larger than Earth that have raged for centuries, that possesses a magnetic field so powerful it traps radiation in deadly belts around the planet, will not notice this comet's passage in any measurable way whatsoever. The planet will not slow down in its orbit. Its rotation will not change. Its moons will not be affected. The great red spot will continue swirling with the same intensity it has displayed for hundreds of years. Europa's subsurface ocean will continue sloshing beneath its icy crust without any disturbance. Io's volcanoes will keep erupting according to the same tidal forces that have driven them for billions of years. Jupiter will remain, in every sense that matters, completely undisturbed by this encounter. And if that sounds anticlimactic, if that feels like I've just deflated all the drama that the title promised, then you're beginning to understand exactly why sensational headlines are so misleading. Because the shock here, the thing that should genuinely surprise you, is not that something dramatic will happen to Jupiter. It's that Jupiter's gravitational influence will dramatically affect the comet while the planet itself remains utterly unchanged. It's the perfect demonstration of something fundamental about how gravity works at cosmic scales, about how mass determines gravitational dominance, about why planets are called planets and comets are called comets. To understand this, you need to grasp a concept that astronomers call the Hill sphere, though don't worry, I'm not going to drown you in technical jargon or complex equations. The Hill sphere is simply the region of space around any celestial body where that body's gravity dominates over other gravitational influences. For Jupiter, this sphere is enormous, extending millions of kilometers in every direction, a vast bubble of gravitational influence where Jupiter's pull is stronger than the Sun's, where objects feel the giant planet's presence more intensely than any other force in the solar system. When 3I Atlas approaches Jupiter's Hill sphere, it will be entering a region where the planet's gravity becomes the dominant force shaping its trajectory. The Sun's gravity is still there, still pulling, still influencing the comet's overall path through the solar system. But in this localized region, Jupiter's pull takes precedence. And because Jupiter is so massive, because it contains more than 300 times the mass of Earth, its gravitational field is powerful enough to significantly alter the trajectory of anything passing through this sphere of influence. This is where the interesting physics comes into play. The comet will approach Jupiter at a specific angle, moving at a velocity that was determined by its interstellar origin and modified by its passage near the Sun. As it enters Jupiter's Hill sphere, the planet's gravity will begin pulling on it, accelerating it slightly, bending its path. The closer it gets to Jupiter, the stronger this effect becomes, until at the point of closest approach, the comet's trajectory will curve dramatically, swinging around the planet in what's called a gravitational slingshot. Now, this slingshot effect is something we've used deliberately with spacecraft. When we send probes to the outer solar system, we often route them past Jupiter specifically to take advantage of this gravitational boost. The spacecraft approaches Jupiter on one trajectory and leaves on a different one, moving faster than it was before, having essentially stolen a tiny fraction of Jupiter's orbital momentum. The planet loses that same amount of momentum in the exchange, but because Jupiter is so enormous, the loss is immeasurably small. The spacecraft gains a significant velocity boost. Jupiter's orbit remains unchanged. The same principle applies to 3I Atlas. The comet will approach on one trajectory and depart on a different one. Its velocity will change, its direction will shift, and if we could measure precisely enough, we would see that Jupiter's orbital velocity decreased by an infinitesimally small amount to account for this change. But that decrease is so tiny, so astronomically insignificant compared to Jupiter's total momentum, that it might as well not exist. Jupiter won't notice. Its orbit won't change. Nothing about the planet's motion through space will be affected in any way we could measure, but the comet will notice. Oh, the comet will absolutely notice. Its path through space will be permanently altered by this encounter. The direction it's travelling will shift, possibly by several degrees, redirecting its future journey through interstellar space toward a different region of the galaxy than it would have reached otherwise. Its velocity relative to the Sun will change, either increasing or decreasing depending on the exact geometry of the encounter, and this change will determine how quickly it escapes our solar system and begins its next multi-million-year voyage through the cosmic void. This is what's actually happening during the encounter. Not a collision, not a planetary disaster, not some catastrophic event that will reshape our solar system. Just a comet passing through a gravity well, responding to forces that have governed celestial mechanics since the universe began, following laws of physics that we understand deeply and can predict with remarkable accuracy. The comet gets redirected. Jupiter continues on, utterly indifferent to the visitor that just passed through its neighbourhood. And from a scientific perspective, this is valuable beyond measure. Because every time we observe one of these gravitational interactions, every time we watch an object pass through a planetary Hill sphere and measure how its trajectory changes, we're testing our understanding of gravity. We're confirming that the equations work, that the predictions hold, that our models of celestial mechanics align with observable reality. For interstellar objects like 3I Atlas, we're also learning how these visitors respond to encounters with giant planets, information that will be crucial if we ever want to predict the paths of future interstellar comets or asteroids that might pass through our solar system. There's also tremendous value in studying what happens to the comet itself during this encounter. Jupiter's gravity might trigger increased outgassing from the comet's surface, causing it to brighten temporarily as ices vaporize and stream away in glowing tails. The tidal forces, the difference in gravitational pull between the side of the comet facing Jupiter and the side facing away, might stress the comet's structure, potentially causing fractures or even breaking it into multiple pieces if the nucleus is weak enough. These effects won't harm Jupiter in any way, but they'll give us unprecedented data about the structural integrity and composition of interstellar comets. Spacecraft like Juno, which has been orbiting Jupiter since 2016, might be positioned to contribute observations during the encounter. While Juno's primary mission is studying Jupiter itself, studying the planet's atmosphere, magnetic field, and interior structure, the spacecraft's instruments could potentially be directed toward 3I Atlas if the geometry works out favourably. Even distant observations, views of the comet from Juno's perspective against the backdrop of Jupiter's cloud tops, could provide valuable context and help triangulate the comet's exact position at the moment of closest approach. Ground-based telescopes will certainly be watching. Every major observatory with the capability to track fast-moving objects will be pointed at this region of space in March 2026, capturing images, measuring spectra, analysing the light reflected and emitted by the comet as it swings past the giant planet. These observations will be compared with data from the earlier Earth and Mars flybys, allowing scientists to track how the comet's activity level changes as it moves through different regions of the solar system, responding to varying levels of solar heating and gravitational stress. But here's where we need to shift our focus, because there's something about this encounter that goes beyond simple gravitational mechanics, something that transforms it from a routine, if rare, observational opportunity into a genuine puzzle that has astronomers scratching their heads and running calculations repeatedly to make sure they haven't made an error. Because the trajectory that 3I Atlas is following, the path that will bring it past Jupiter with such precision, reveals something unexpected about how this comet is moving through space. And that something is what actually shocked scientists when they first noticed it in the data. There's a moment in every scientific investigation when the data stops simply confirming what you expect and starts showing you something you didn't anticipate. It's the moment when routine measurements become unexpected discoveries, when numbers on a screen transform from predictable patterns into genuine mysteries demanding explanation. For the scientists tracking 3i Atlas, that moment came when they refined their trajectory calculations after months of careful observation and realized that this comet's path through our solar system was precise in ways that natural celestial mechanics rarely produce. Let me explain what precision means in the context of orbital mechanics, because it's not quite the same as precision in everyday life. When we calculate the trajectory of any object moving through space, we're dealing with massive uncertainties. Space is vast, velocities are enormous, and tiny measurement errors can compound into significant uncertainty about where an object will be at any future date. When astronomers first detect a new comet or asteroid, their initial orbit calculations usually come with substantial error bars, margins of uncertainty that might span thousands or even millions of kilometers, depending on how much observational data they have to work with. As observations accumulate, as more telescopes track the object from more angles over longer time periods, those error bars shrink. The calculated trajectory becomes more precise, more refined, more confident. Eventually, for well-observed objects, we can predict positions weeks or months in advance with accuracy measured in kilometers rather than thousands of kilometers. It's an impressive demonstration of mathematical modeling and observational astronomy working together to map the motion of objects across the solar system. But here's what makes 3i Atlas unusual. As scientists gathered more data, as they refined their calculations of the comet's trajectory, they discovered that it wasn't just approaching Jupiter, it was approaching along a path that threaded through a very specific region of space, with almost perfect precision. The distance at closest approach, the angle of the flyby, the velocity at that moment, all of these parameters were aligning in ways that suggested an almost engineered quality to the trajectory, as if someone had calculated the optimal path for a close Jupiter encounter and then placed the comet on exactly that course. Now, before your mind jumps to extraordinary explanations, let me be clear about what I'm saying and what I'm not saying. I am not suggesting that this comet was deliberately aimed at Jupiter by some intelligence. I am not proposing that aliens are steering it, or that we're witnessing evidence of extraterrestrial technology. What I am saying is that the precision of this trajectory is statistically unusual enough that it demands scientific explanation, and that explanation needs to account for forces beyond simple gravity. In orbital mechanics, there's a concept called trajectory optimization. When space agencies plan missions to other planets, they use complex calculations to determine the most efficient path, the route that requires the least fuel, that arrives at the target at the right time, that positions the spacecraft for whatever observations or maneuvers it needs to perform. These optimized trajectories thread through gravitational keyholes, passing planets at specific distances and angles to maximize scientific return while minimizing risk and resource expenditure. What's unusual about 3i Atlas is that its trajectory resembles one of these optimized paths, except no one designed it. No space agency calculated this route. No engineers spent years planning the flyby geometry. This comet simply emerged from interstellar space, already on a course that would bring it past Earth, then Mars, then Jupiter, with each encounter happening at distances and angles that seem almost too convenient, too precise, too mathematically elegant to be purely coincidental. And this precision became even more apparent when scientists factored in something called non-gravitational acceleration. You see, comets aren't simply inert chunks of ice and rock, following perfectly predictable orbits determined solely by gravity. As they approach the Sun and warm up, ices on their surface and in their interior begin to vaporize, creating jets of gas and dust that stream away from the nucleus. These jets act like tiny rocket engines, producing thrust that alters the comet's trajectory in ways that pure gravitational models can't predict. For most comets, these non-gravitational forces are chaotic and unpredictable. Jets fire in random directions as different patches of surface warm up at different times. The comet's rotation causes these jets to sweep around like a spinning lawn sprinkler, creating acceleration in constantly changing directions. The net effect is usually a slight deviation from the purely gravitational orbit, but one that's difficult to model accurately without detailed knowledge of where the jets are located and how they're oriented relative to the comet's spin axis. What makes 3i Atlas remarkable is that its non-gravitational acceleration appears to be anything but chaotic. When scientists detected this acceleration, when they measured the subtle changes in velocity that couldn't be explained by gravity alone, They found that these changes seemed to be reinforcing the precision of the Jupiter trajectory rather than degrading it. It was as if the jets, the outgassing, the non-gravitational forces were all conspiring to keep the comet on its mathematically elegant path, rather than pushing it randomly away from that path. Think about what this means for a moment. Natural processes, the random warming and outgassing of an icy surface, are somehow producing thrust in directions that maintain trajectory precision, rather than destroying it. It's like throwing a dart and having wind gusts along its flight path somehow correct its course, rather than blowing it off target. It's possible, certainly, but it's unusual enough that it demands explanation. Several hypotheses have been proposed to account for this precision. The most conservative explanation is that we're simply witnessing a fortunate coincidence that the jets happen to be oriented in ways that maintain the trajectory by pure chance, and that our sense of the precision being unusual is more a result of human pattern seeking than actual statistical anomaly. After all, humans are exceptionally good at finding patterns even in random data, at seeing significance in coincidences that are actually just the natural outcome of probability playing out across many events. Another possibility is that the non-gravitational acceleration is actually more symmetric than it appears. If the comet has multiple jets firing in roughly balanced directions, the net acceleration might be small and relatively stable, producing predictable changes that can be modelled and incorporated into trajectory calculations. This would explain why the path remains precise, the outgassing is real and measurable, but its effects are sufficiently predictable that they don't introduce the kind of chaotic variations we see in many other comets. A more intriguing hypothesis suggests that the comet's rotation rate and axis orientation might be special in some way. If the comet is spinning at just the right speed, with its rotation axis aligned in just the right direction, the outgassing jets might average out over each rotation to produce a very stable and predictable acceleration vector. This would be unusual but not impossible, a circumstance where the comet's physical properties happen to align in ways that minimize trajectory uncertainty. What we don't know, what remains genuinely mysterious, is which of these explanations is correct, or whether the truth involves some combination of factors we haven't fully considered yet. And this uncertainty is what transforms the March 2026 encounter from a simple observational event into a critical test of our understanding. Because during that close approach to Jupiter, we'll be able to measure the comet's properties with unprecedented precision. We'll be able to track exactly how its trajectory changes, how much non-gravitational acceleration occurs, whether the precision is maintained or degraded as it threads through Jupiter's gravity well. The numbers that initially revealed this precision came from careful analysis of positional measurements gathered over many months. Astronomers compared where the comet actually appeared in the sky with where gravitational models predicted it should appear, and the discrepancies, while small, were consistent and pointed toward non-gravitational effects. When they incorporated those effects into refined models, the trajectory they calculated showed this remarkable precision in the Jupiter approach, this threading of a gravitational keyhole that natural processes rarely achieve. And here's what makes this so scientifically valuable. If we can understand why this particular comet exhibits such trajectory precision, we'll gain insights into how interstellar objects behave during their brief passages through planetary systems. We'll learn about the relationship between cometary outgassing and orbital stability. We'll develop better models for predicting the paths of future interstellar visitors, which could be crucial if one of those visitors ever appears to be on a collision course with Earth, and we need to calculate whether it's actually a threat or just another precise but harmless flyby. The precision revealed by these calculations is what genuinely shocked the astronomical community, not because it suggested anything impossible, but because it highlighted how much we still have to learn about the forces that shape cometary trajectories. It's a reminder that even in a field as mature as orbital mechanics, even with centuries of observations and refinement of gravitational theory, nature can still surprise us with phenomena that sit right on the edge of what our current understanding predicts. So as we approach March 2026, as telescopes around the world prepare to capture this encounter in unprecedented detail, scientists aren't just hoping to observe a comet passing a planet. They're hoping to solve a mystery, to understand why this particular trajectory exhibits this particular precision, and to learn what that precision tells us about the physics governing these cosmic travelers from beyond our solar neighborhood. But to appreciate the depth of this mystery, we need to look more closely at the steering mechanism itself, at the forces that might be guiding 3I Atlas along its mathematically elegant path. When you hear the word steering applied to a comet, your mind might immediately jump to intentional guidance, to some form of control being exerted over the object's trajectory. And I want to address that natural instinct directly, because while the precision of 3I Atlas's path might seem to suggest deliberate direction, the scientific community is focused on understanding natural mechanisms that could produce this effect, mechanisms that operate according to known physics but in ways we're still working to fully characterize and predict. Cometary steering through non-gravitational forces is actually a well-established phenomenon, though the details of how it works remain complex and sometimes poorly understood. Every comet that approaches the Sun experiences this to some degree. As solar radiation heats the nucleus, frozen volatiles, primarily water ice but also carbon dioxide, methane and other compounds, sublimate directly from solid to gas without passing through a liquid phase. This vaporization creates pressure beneath the surface that eventually erupts through weak points in the crust, forming jets that spray gas and dust into space at velocities measured in hundreds of meters per second. These jets are essentially natural rocket engines. They produce thrust, they accelerate the comet, and depending on where they're located on the nucleus and which direction they're pointed, they can push the comet in essentially any direction, speeding it up, slowing it down, or deflecting it sideways relative to its orbital path. For a small comet with relatively low mass, even modest outgassing can produce measurable changes in velocity over time, changes that accumulate into significant trajectory alterations over months or years. The challenge in predicting these effects lies in the complexity of the system. A comet's nucleus is not a uniform sphere with predictable properties. It's an irregular chunk of ice and rock with varying composition, varying strength, varying thermal properties. Some regions might be rich in highly volatile ices that vaporize easily. Other regions might be covered in a thick dust layer that insulates the interior and prevents outgassing. The distribution of these properties across the surface is essentially unknowable without a close-up mission to map the nucleus in detail. Furthermore, the comet is rotating, tumbling through space as it orbits, and this rotation means that any given jet is constantly changing its orientation relative to the direction of motion. A jet that points forward for part of the rotation, slowing the comet down, will point sideways or backward at other times, producing acceleration in different directions. The net effect depends on the complex interplay of rotation rate, jet locations, jet strengths, and the comet's orbital position relative to the Sun. For most comets we study, these non-gravitational accelerations introduce uncertainty into trajectory predictions. We can measure the overall effect by comparing observed positions with purely gravitational orbits, but predicting future acceleration requires modeling the outgassing in detail, which is extremely difficult without direct imaging of the nucleus showing us where the active regions are located. This is why long-period comets, objects that spend most of their time in the outer solar system, where they're cold and inactive, often surprise us when they return to the inner solar system and begin outgassing, their trajectories deviating from predictions in ways we couldn't fully anticipate. What makes 3I Atlas unusual is that despite experiencing detectable non-gravitational acceleration, despite the outgassing that's been observed through brightening and the development of a faint tail, its trajectory has remained remarkably stable and predictable. The acceleration doesn't seem to be introducing the kind of chaotic variations we often see with other comets. Instead, it seems to be acting in ways that maintain or even enhance the precision of the Jupiter approach, as if the forces are balanced in some special configuration. One possibility that scientists are exploring is that this comet might have an unusually symmetric outgassing pattern. If the nucleus has active regions distributed relatively evenly around its surface, and if those regions have similar strengths, the jets they produce might cancel each other out to a large degree. The comet would still experience net acceleration, but that acceleration would be relatively constant in direction and magnitude, making it predictable and modelable even without detailed knowledge of the surface properties. This kind of symmetry is rare but not impossible. It would require the comet's formation and evolutionary history to have produced a nucleus with balanced composition and structure, perhaps through repeated heating and cooling cycles during its time in its original star system, or through collisional processing that fractured and mixed its interior before it was ejected into interstellar space. If such symmetry exists, 3I Atlas might represent an unusually well-behaved example of an interstellar comet, one whose outgassing follows more predictable patterns than the chaotic behavior we've come to expect from these objects. Another intriguing possibility involves the comet's rotation state. All comets rotate, but the rate of rotation and the orientation of the spin axis vary widely. Some comets spin rapidly, completing a rotation in hours. Others rotate slowly, taking days to turn once. The spin axis can point in any direction, sometimes aligned with the orbital plane, sometimes perpendicular to it, sometimes at odd angles that produce complex tumbling motions. For 3I Atlas, if the rotation happens to be particularly stable, with a well-defined axis and a moderate rotation period, the outgassing jets might average out in a way that produces steady acceleration. Imagine a comet with jets near its equator, distributed roughly evenly around the circumference. As the comet rotates, each jet takes a turn pointing in different directions, but over a complete rotation, the sum of all those thrust vectors might point consistently in one direction, perhaps along the spin axis or perpendicular to it. This configuration would produce predictable acceleration that could be modelled and incorporated into trajectory calculations. This scenario becomes even more interesting when you consider how the comet's orientation might have been established during its interstellar journey. Objects drifting through space for millions of years experience extremely subtle influences, tidal effects from passing stars, pressure from the interstellar medium, even radiation pressure from cosmic rays. These forces are incredibly weak, but acting over geological timescales, they might be sufficient to gradually alter rotation states, damping out chaotic tumbling and settling the object into a more stable spin configuration. If 3I Atlas underwent this kind of stabilization during its interstellar voyage, it might have arrived in our solar system with rotation properties that naturally lead to predictable outgassing behavior. There's also the question of composition. Not all comets are created equal. Some are rich in highly volatile ices like carbon monoxide and methane, which vaporize even at great distances from the Sun, producing early and vigorous outgassing. Others are dominated by water ice, which requires more heating to sublimate and produces more moderate outgassing closer to the Sun. Still others might have complex mixtures with varying proportions of different ices, leading to changing activity patterns as the comet moves through its orbit. If 3I Atlas has a composition that leads to relatively gentle, sustained outgassing rather than explosive bursts, that could contribute to trajectory stability. A comet that releases gas steadily, without dramatic variations in activity level, will experience more consistent acceleration than one that alternates between quiescent periods and violent outbursts. And if this comet formed in a region of its home star system that had a different composition than our own solar system's comet-forming regions, different ratios of elements and molecules in the original protoplanetary disk, it might indeed have unusual compositional properties that affect its behavior. The scientific community is also considering more exotic possibilities, though these remain speculative pending additional data. One hypothesis suggests that the comet might have experienced a major outgassing event early in its passage through our solar system, perhaps during its closest approach to the Sun, that altered its rotation state in a favourable way. Large jets firing asymmetrically can produce torques that change how a comet spins, and if such an event happened to spin the comet up or down to a more stable configuration, it could explain why subsequent outgassing has been so predictable. Another idea involves the possibility that the comet's nucleus might be binary or multiple, two or more objects orbiting their common centre of mass while also orbiting the Sun. Binary comets are known to exist, and their dynamics can be complex. If 3I Atlas is a binary system with components that have complementary outgassing patterns, the net acceleration might be more stable than what either component would produce individually. This scenario is difficult to verify without high-resolution imaging that can resolve the nucleus into separate components, which is challenging given the comet's small size and current distance. What all of these hypotheses share is an attempt to explain precision through natural physics, through the complex but understood interactions of thermal processes, outgassing dynamics, rotation mechanics, and gravitational influences. None of them require invoking unknown forces or extraordinary explanations. They simply represent different configurations of known phenomena that could, under the right circumstances, produce the observed trajectory precision. But here's what makes this genuinely mysterious from a scientific standpoint. We don't yet know which explanation is correct. We don't have enough data about the comet's detailed properties to distinguish between these possibilities. We can measure the net acceleration, we can track how the trajectory evolves, but without close-up observations showing us the nucleus surface, the jet locations, the rotation state, and the composition, we're essentially watching the outcome without seeing the mechanism. This is where the March 2026 encounter becomes crucial. During the Jupiter flyby, the comet will experience significant gravitational stress. Jupiter's tidal forces, the difference in gravitational pull across the nucleus, might trigger new outgassing, might alter existing jet patterns, might even cause structural changes if the nucleus is fragile. Observing how the comet responds to these stresses will provide valuable clues about its internal structure and composition. The encounter will also occur at a point in the comet's orbit where solar heating is moderate, neither extremely intense nor completely absent. This means outgassing should be active but not violent, allowing clear observations of how the jets behave under relatively controlled conditions. Telescopes will be able to photograph the comet against the backdrop of Jupiter, using the planet as a reference point to precisely measure position and velocity changes in real time. If the comet's trajectory remains precise through the encounter, if the non-gravitational acceleration continues to act in predictable ways even as Jupiter's gravity dramatically alters the overall path, that will provide strong evidence for an underlying stability in the outgassing process, whether due to symmetry, rotation configuration, or compositional properties. If, on the other hand, the encounter triggers chaotic behavior, if jets start firing unpredictably and the trajectory precision breaks down, that will tell us something different, that the stability we've observed so far was circumstantial rather than intrinsic, dependent on conditions that don't hold during close planetary approaches. What scientists are really hoping to understand through all of this is how interstellar comets differ from their solar system counterparts. Do objects that formed around other stars in different chemical environments, with different thermal histories, behave fundamentally differently when they enter new stellar environments? Or are comets so similar across different planetary systems that the basic physics remains the same regardless of origin? 3i Atlas represents one of our first opportunities to answer these questions. With only 3 confirmed interstellar objects detected so far, and with Oumuamua and Borisov each presenting their own unique puzzles, every additional data point matters enormously. If this comet's precision and stability turn out to be common features of interstellar visitors, that tells us something profound about how these objects are shaped by their journeys through the galaxy. If it turns out to be unusual even among its interstellar peers, that makes it an outlier worth studying in even greater detail. The steering mystery, then, is not about whether something artificial is guiding this comet. It's about understanding the natural mechanisms that can produce guidance-like precision without any intention or design. It's about mapping the parameter space of cometary behavior, identifying the conditions under which outgassing can stabilize rather than destabilize trajectories, and learning to predict which comets will follow neat, modelable paths and which will surprise us with chaotic unpredictability. And the answers to these questions are waiting for us in March 2026, when 3i Atlas threads its way past Jupiter and gives us one final, close-up look before it vanishes back into the interstellar void. March of 2026 is going to be an extraordinary month for anyone who follows astronomy and planetary science, because we're going to witness something that hasn't happened in recorded human history at quite this level of observational readiness. An interstellar visitor, an object that came from beyond our solar system, will make its closest approach to the largest planet we know, and we'll be watching with every tool and instrument we have available, capturing data that will be analysed for years to come and that will fundamentally shape our understanding of these cosmic travellers. The beauty of modern astronomy is that we know this event is coming. Unlike sudden supernovae or unexpected asteroid discoveries that force scientists to scramble for observing time and quickly redirect telescopes, the Jupiter encounter with 3i Atlas has been on the calendar for months. Observatories around the world have had time to plan their observing campaigns, to schedule time on major instruments, to coordinate international collaborations that will ensure continuous coverage throughout the critical hours when the comet is closest to the planet. Ground-based telescopes will bear the bulk of the observational workload. Facilities like the Keck Observatory in Hawaii, the Very Large Telescope in Chile, the Gemini telescopes in both hemispheres, these powerful instruments with their enormous light-gathering capacity and sophisticated imaging systems will be pointed at the Jupiter region throughout the encounter period. They'll capture images showing the comet's position relative to Jupiter's disk, tracking its motion across the field of view with the kind of precision that allows trajectory calculations accurate to within tiny fractions of the comet's actual path. Spectroscopy will be crucial. By splitting the light from the comet into its component wavelengths, creating a spectrum that shows which colours are present and which are absorbed, Astronomers can determine what molecules are present in the outgassing, how abundant they are, and how their concentrations change as the comet responds to Jupiter's gravitational influence and any associated heating or tidal stress. These spectra will reveal the comet's composition in remarkable detail, showing us whether its chemical makeup resembles solar system comets, or whether it has exotic abundances that reflect formation in a different stellar environment. Polarimetry, the measurement of how light is polarized as it reflects off the comet's surface and scatters through its dust coma, will provide information about particle sizes and properties in the material being shed by the nucleus. This technique can distinguish between different types of dust grains, revealing whether the comet is releasing pristine particles from its interior or recycled material that's been processed by previous heating cycles. Such information speaks to the comet's history, to how many times it might have approached a star before this current passage through our solar system. Radio telescopes might also contribute, though their role will be more specialized. Some comets produce detectable radio emissions from molecules like water and hydroxyl radicals in their comae, and if 3I Atlas is active enough, radio observations could provide unique data about the outgassing rate and the distribution of material around the nucleus. These observations are sensitive to different aspects of cometary behavior than optical telescopes, offering complementary insights that fill gaps in our understanding. The real wildcard in all of this is Juno. This NASA spacecraft has been orbiting Jupiter since 2016, conducting an extended mission to study the planet's atmosphere, magnetic field, interior structure, and radiation environment. Its highly elliptical orbit carries it from close passes that skim just above the cloud tops to distant excursions that take it far from the planet before swinging back in for another close approach. The geometry of Juno's orbit in March 2026 will determine whether the spacecraft has any opportunity to observe 3I Atlas during the encounter. If the timing works out favourably, if Juno happens to be in a position where it can see the comet without compromising its primary science objectives, studying Jupiter, mission controllers might authorize special observations. These wouldn't be detailed close-up images like we would get from a dedicated comet mission. Juno wasn't designed for that purpose, and its instruments are optimized for planetary rather than cometary science. But even distant observations from a spacecraft perspective would be valuable, providing a different viewing angle than Earth-based telescopes, potentially resolving details that are blurred together when seen from our planet's distance. The real value of any Juno observations would be contextual. Seeing the comet from two different locations simultaneously, from Earth and from Jupiter orbit, allows triangulation that pins down the comet's exact position with greater accuracy than single location observations can achieve. This positional data feeds directly into trajectory refinement, helping scientists understand precisely how Jupiter's gravity altered the comet's path and whether any non-gravitational effects were triggered by the encounter. What scientists are most hoping to see during the encounter is evidence of activity changes. If Jupiter's tidal forces stress the comet's nucleus, if the gravitational gradient across the object produces tension that opens new cracks or activates dormant vents, we might see a sudden brightening as fresh outgassing begins. This would appear in telescopic observations as an increase in the comet's brightness, the development of new features in its coma, possibly even the formation of a more prominent tail, as increased dust and gas production creates more visible structures. Such activity changes would be scientifically valuable because they would reveal how structurally cohesive the nucleus is. A comet that responds dramatically to tidal stress is probably loosely bound, perhaps a rubble pile held together more by its own weak gravity than by any internal strength. A comet that passes through the encounter without significant activity changes is likely more solid, with internal cohesion that resists tidal disruption. This distinction matters for understanding how these objects survive their journeys through the galaxy, whether they're fragile assemblages that barely hold together or robust chunks of frozen material that can withstand gravitational stress from repeated stellar encounters. The trajectory data will be equally important. By comparing the comet's position before, during, and after the Jupiter encounter, astronomers will measure exactly how much the planet's gravity deflected the path, how much the velocity changed, and whether these changes match theoretical predictions. Any discrepancies between observation and theory would be fascinating, suggesting either that our gravitational models need refinement or that non-gravitational effects played a larger role than expected. These trajectory measurements will also determine the comet's ultimate fate with much greater precision than current estimates allow. Right now, We know 3i Atlas is on a hyperbolic orbit that will carry it out of the solar system, but the exact direction of its departure, the velocity it will have when it's far from the Sun's influence, and consequently the region of the galaxy it will head toward, all depend sensitively on what happens during the Jupiter encounter. The gravitational slingshot effect will be measurable and significant, potentially altering the comet's final trajectory by degrees that translate to vast differences in destination over interstellar distances. Amateur astronomers will have a role to play as well. While professional observatories will capture the highest quality data, amateur telescopes around the world will provide additional coverage, filling gaps when professional instruments are pointed elsewhere or when weather conditions prevent observations at major facilities. The amateur astronomy community has grown remarkably sophisticated in recent decades, with access to imaging equipment and analysis software that would have been professional grade just a generation ago. Their contributions to cometary science are real and valued, and 3i Atlas will benefit from their attention. Public engagement will be part of the story too. Space agencies and observatories typically release images and updates during major astronomical events, and the Jupiter encounter will certainly receive this treatment. We'll likely see processed images showing the comet as a faint smudge near Jupiter's bright disk, animations tracking its motion across multiple nights of observation, perhaps even colour-coded maps showing how the comet's composition or structure changes during the flyby. These public releases serve the dual purpose of sharing science with a broader audience and maintaining public support for the astronomical research that makes such discoveries possible. What's particularly exciting about this event from a timing perspective is that we're living in an era with the technology and the organisational capacity to study it properly. A century ago we might have noticed an interstellar comet passing through our solar system, but we wouldn't have had the instruments to characterise it in detail, or the computational tools to model its trajectory with precision. A century from now we'll presumably have even better capabilities, perhaps even spacecraft that can be rapidly dispatched to intercept interstellar visitors for close-up study. But right now, in 2026, we're at a sweet spot where our observational capabilities are sophisticated enough to extract real science from this encounter, while the rarity of the event still makes it genuinely special and noteworthy. The data collected during those critical hours in March will be archived and studied for years. Initial results will be published within months as researchers rush to analyse what they observed and compare it with predictions. But deeper analysis, comparing this event with future interstellar visitor encounters, synthesizing the data into comprehensive models of cometary behaviour, will continue for decades. Every future interstellar comet we detect will be compared with 3i Atlas, and the Jupiter encounter data will serve as a benchmark for understanding how these objects interact with giant planets. And then, after all the telescopes have captured their images, after all the spectra have been recorded and the trajectories measured, 3i Atlas will continue on its way, departing Jupiter's neighbourhood and heading toward the outer solar system, beginning the final leg of its journey through our cosmic region, before returning to the interstellar medium from which it came. And that departure, that final farewell, carries its own significance and raises its own questions about what comes next for this ancient traveller. After the drama of the Jupiter encounter fades, after the telescopes have captured their final images and the comet recedes from the giant planet's neighbourhood, 3i Atlas will continue on a trajectory that leads to only one possible destination. Oblivion is too strong a word, but departure comes close. This comet is leaving our solar system, not temporarily like a long-period comet that will return in thousands of years, but permanently, forever, on a one-way journey back into the interstellar void. The trajectory after Jupiter will carry it outward through the outer solar system, past the orbits of Saturn, Uranus, and Neptune, though it won't make any close approaches to these distant worlds. Its path will take it through the increasingly sparse regions where sunlight grows faint and temperatures plunge toward the cosmic background radiation, where the sun becomes just another bright star in the sky, rather than the dominant heat and light source that defines the inner solar system's environment. As it travels outward, the comet will gradually fade from view. The combination of increasing distance and decreasing activity as solar heating drops to negligible levels will make it progressively harder to observe until, eventually, even the most powerful telescopes on Earth or in space will lose track of it against the background of distant stars. There will come a moment, sometime in the years following the Jupiter encounter, when 3i Atlas is observed for the last time by human instruments, captured in a final image as a faint smudge of light that then disappears into the darkness, never to be seen again. the direction of its departure will carry it toward the constellation Gemini as seen from Earth's perspective, though this is merely a line-of-sight description, a statement about which part of the sky it will appear in from our vantage point, rather than a meaningful description of its destination. In truth, the comet isn't heading toward any particular stellar system. It's simply moving through the galaxy on a trajectory that will take millions of years to carry it across even a small fraction of the Milky Way's vast disk. It might eventually encounter another star system, might get captured or perturbed by some future gravitational interaction, but the timescales involved are so enormous that speculation about its ultimate fate becomes meaningless. What we can say with confidence is that 3I Atlas will spend the next millions of years essentially alone, drifting through the near-perfect vacuum of interstellar space at a velocity relative to the Sun that ensures it will never return here. The brief period it spent passing through our solar system, the few months when it was close enough and bright enough for us to study, represents a tiny fraction of its existence, a momentary encounter between this ancient wanderer and our temporary observation capabilities. There's something poignant about this finality, this recognition that we're witnessing a one-time event that will never repeat. 3I Atlas came from somewhere we'll never identify, passed through our region of space at exactly the right time for us to notice it, and will depart toward a future we can't predict. In a sense, every interstellar object we detect is a messenger carrying information from distant regions of the galaxy. From stellar systems we may never directly observe, bringing us samples of materials and conditions that existed elsewhere and elsewhen. These are the galaxy's gift to us, opportunities to study cosmic diversity without needing to travel the impossible distances to other star systems. The fact that we're alive during the brief historical window when we have the technology to recognize and study these visitors makes us extraordinarily fortunate. For the vast majority of human history, comets were mysterious and often frightening apparitions, omens interpreted through mythology and superstition rather than understood through science. Even when we developed telescopes and began systematic astronomical observations, we lacked the understanding to recognize that some comets might be interstellar, might come from beyond the Sun's gravitational domain. Only in the last few decades have we gained the observational precision and theoretical framework to identify these visitors definitively, and we're still in the early stages of this capability. 3I Atlas is only the third confirmed interstellar object we've detected. There have probably been others that passed through unnoticed, either too faint to observe, moving through parts of the sky we weren't monitoring, or arriving before we had the technology to recognize their interstellar nature. And there will certainly be more in the future, more visitors from distant stellar systems, each carrying its own unique properties and raising its own set of questions about what exists beyond our immediate cosmic neighborhood. What we learn from 3I Atlas, the data we gather during its passage and especially during the Jupiter encounter, will inform how we study these future visitors. We'll have a better sense of what to look for, what measurements to prioritize, what observations are most scientifically valuable. We'll refine our models of interstellar object behavior, understanding how they respond to gravitational interactions with planets, how their outgassing patterns evolve as they move through different regions of a stellar system, how their trajectories can be predicted despite the complications of non-gravitational forces. This accumulated knowledge will eventually enable more ambitious missions. There have already been proposals for rapid response spacecraft that could be launched to intercept interstellar visitors, matching their trajectories and conducting close-up studies that ground-based observations can never achieve. These concepts face enormous technical challenges, the velocities involved are extreme, the launch windows are brief, and the navigation requirements are demanding, but they're not impossible, and as our detection capabilities improve as we get better at spotting interstellar objects early in their passage through the solar system, the feasibility of such missions increases. Imagine a future where, instead of watching 3I Atlas from hundreds of millions of kilometers away, we could send a probe that flies alongside it, imaging its nucleus in detail, measuring its composition directly, tracking exactly how jets fire and how they affect the trajectory. That level of investigation would transform our understanding from indirect inference to direct observation, answering in hours or days questions that currently require years of careful analysis and sophisticated modeling. But even without such missions, even with just the ground-based and potentially Juno observations we'll gather in March 2026, 3I Atlas will leave us with a richer understanding of the cosmos. It will contribute data points to our growing catalogue of interstellar objects, helping us understand whether they're fundamentally similar to solar system comets or whether their different origins produce meaningfully different properties. It will test our models of orbital mechanics and non-gravitational forces in extreme conditions we rarely get to observe, and it will remind us that our solar system is not isolated, that it exists within a galaxy full of other systems, some of which occasionally send us visitors carrying information from worlds we'll never otherwise know. The journey that brought this comet here spanned distances we struggle to comprehend and timescales that dwarf human civilization. The journey that will carry it away will be equally vast, equally lonely, a return to the darkness between stars where it spent most of its existence. Our encounter with it is the briefest of interruptions in that cosmic wandering, a moment of mutual observation between human instruments and ancient ice, a fleeting opportunity to learn something about the universe beyond our immediate neighbourhood. And when it's gone, when the last observation has been recorded and the comet has faded beyond detection, we'll be left with our data, our measurements, our analyses, and our questions. Some of those questions will have answers, explanations for the precision we observed, understanding of the forces that shaped its trajectory. But others will remain open, mysteries that even the Jupiter encounter couldn't fully resolve, puzzles that await future visitors and better observations to illuminate. And that's how science progresses, not through complete answers that close all questions, but through partial understanding that reveals deeper mysteries and motivates continued investigation. Science is often portrayed as a process that produces certainties, definitive answers that settle questions once and for all. But the reality is far more nuanced and, honestly, far more interesting. Science is better understood as a process that transforms vague uncertainties into precise questions, that replaces ignorance with partial understanding, and that reveals layers of complexity beneath what initially seemed simple. 3i Atlas embodies this reality perfectly, because even after all the observations, all the calculations, all the careful analysis, we're left with a mixture of things we know, things we think we know, and things that remain genuinely mysterious. Here's what we know with high confidence. This is an interstellar object, a comet that formed around a star other than our Sun, and that travelled through the galaxy before entering our solar system. Its trajectory is hyperbolic, meaning it's moving too fast for the Sun's gravity to capture it permanently, and it will leave our system after completing this single pass through the inner planets. It has made close approaches to Earth and Mars already, and in March 2026 it will make a close approach to Jupiter. None of these encounters pose any danger to the planets involved. Jupiter will remain completely unaffected. The comet will be gravitationally deflected and will continue outward toward interstellar space. We also know that the comet exhibits non-gravitational acceleration, subtle changes in its trajectory that can't be explained by gravity alone, and that are almost certainly due to outgassing, as solar heating vaporizes ices from the nuclear surface. This behavior is entirely normal for comets, and is expected for an object like 3i Atlas as it moves through the inner solar system. The outgassing produces jets that act like weak rocket engines, altering the comet's path in small but measurable ways. What we think we know, but with less certainty, is that this outgassing is producing an unusually stable and predictable effect on the trajectory. The comet's path appears to be more precise than random jet orientations would typically produce, threading through what could be described as a gravitational keyhole near Jupiter, with accuracy that seems remarkable. This precision suggests that something about the comet's properties, perhaps its rotation state, perhaps its composition, perhaps the distribution of active regions on its surface, is creating more ordered behavior than we usually observe in cometary outgassing. But here's where honest scientific assessment requires acknowledging uncertainty. We don't actually know for certain that this precision is as unusual as it appears. Our sample size of well-observed interstellar comets is tiny, just 3 objects, and our understanding of normal variability in cometary behavior is still incomplete. It's possible that what we're seeing with 3i Atlas is actually more common than we realize, and our sense of its uniqueness reflects our limited experience rather than genuine anomaly. We need more examples, more interstellar visitors, more opportunities to observe and compare before we can confidently say whether this comet is truly special or simply the first time we've looked carefully enough to notice behavior that occurs regularly. We also don't know for certain what mechanism is producing the trajectory precision. The hypotheses about symmetric outgassing, stable rotation, compositional properties, These are educated guesses based on our understanding of cometary physics, but they remain unverified. The March 2026 observations might help narrow down the possibilities, might provide evidence that strongly favours one explanation over others, but they might not. We might end up with more data points, but still lacking the smoking gun evidence that definitively answers the question. And then there are the deeper mysteries, the questions that this event raises but can't answer on its own. Where exactly did 3I Atlas come from? Not just the general direction in the Sagittarius region, but the specific star system, the specific planetary environment where it formed. Given its velocity and trajectory, we can backtrack its motion through the galaxy and identify regions of space it might have passed through millions of years ago. But pinpointing an origin requires accuracy we simply don't have. Interstellar space is vast, stellar, systems are numerous, and the uncertainties in our trajectory calculations make it impossible to say, this comet definitely came from that specific star. What was the process that ejected it from its home system? Was it a violent event, a stellar death, or a close encounter between stars that disrupted planetary orbits? Or was it a gradual process, slow gravitational perturbations that eventually gave this chunk of ice enough velocity to escape? Both scenarios are plausible, both have precedent in our understanding of stellar and planetary dynamics, but we have no way to determine which actually occurred for this particular object. How many other interstellar objects are passing through our solar system right now that we haven't detected? Our observational surveys have improved dramatically in recent decades, but we're still only sampling a fraction of the sky at any given time. Smaller objects, fainter objects, objects moving through regions we're not currently monitoring, could easily pass through unnoticed. Statistical models suggest there might be multiple interstellar visitors in the inner solar system at any given time, but we're only seeing the brightest, most convenient examples. What are we missing, and what could those unseen visitors teach us if we had the capability to detect them? And perhaps most intriguingly, what can interstellar objects tell us about planetary system formation and evolution throughout the galaxy? Every comet like 3I Atlas represents a sample of material from another stellar system, a piece of a planet-forming disk that was assembled elsewhere under possibly different conditions. If we could analyse enough of these visitors, if we could characterise their compositions and properties in detail, we might start to see patterns that reveal how common our solar system's composition is, how much variation exists in the materials that build planetary systems, how different the conditions might be around stars of different masses or ages or metallicities. These are questions that push at the boundaries of current capability, that require not just better observations of individual objects, but systematic surveys and statistical analyses of populations. They're questions that will take decades to answer, requiring the detection and characterization of dozens or hundreds of interstellar visitors to build the dataset needed for meaningful conclusions. But that's exactly why events like the March 2026 Jupiter encounter matter. Each observation, each data point, each carefully measured trajectory and spectrum contributes to this long-term project of understanding the galaxy we inhabit. 3I Atlas might not answer all our questions, it certainly won't, but it will answer some and refine others, moving us incrementally closer to comprehensive understanding. And in the meantime, we're left with the profound reminder that the universe still has secrets, that despite all our technological advancement and all our scientific progress, there remain phenomena that surprise us, patterns that we don't fully understand, cosmic visitors that raise more questions than they answer. That's not a failure of science, it's the essence of science, the recognition that understanding is always partial, always provisional, always subject to revision as new evidence emerges. So as we approach March of 2026, as telescopes prepare to capture this encounter in unprecedented detail, we do so with excitement not because we expect complete answers, but because we expect to learn something new, to add another piece to the puzzle, to transform another patch of ignorance into partial understanding that reveals the next layer of mystery waiting beneath. If you've stayed with me through this entire investigation, if you've followed this journey from sensational headlines through careful science to honest acknowledgement of what remains unknown, then you understand why this story matters beyond any single shocking revelation. It matters because it represents how we engage with the cosmos, not through fear or sensationalism, but through curiosity, careful observation, and the patient work of piecing together understanding from fragmentary evidence. I want to invite you to continue following this story as we move toward March 2026. Subscribe to this channel so you don't miss updates when new observations are released, when the encounter happens, when scientists begin sharing their initial findings. And drop a comment below telling me what aspect of this mystery intrigues you most. Is it the trajectory precision, the non-gravitational steering, the interstellar origin, the unanswered questions about where this comet will go after it leaves us? Your perspective matters. Your questions help shape how we explore these topics, and I genuinely want to know what draws you to these cosmic mysteries, because ultimately, science is a conversation, a shared exploration of the universe we all inhabit, and every voice that joins that conversation enriches our collective understanding of the extraordinary cosmos surrounding us.